All right, everybody. Thanks for joining once again for another one of our installments of the HPC workshop series. Thanks for those joining in person, and thanks for those joining online, and thanks for those watching this on YouTube later on. We appreciate all of you for your interest in this topic. Today, we're going to be continuing our topic from last week. We talked about the theory of parallel computing last week, went over a lot of different ideas and concepts from that. Um, so definitely recommend checking that out if you haven't done so yet, just because it is going to be relevant to a lot of today's material. But today we're going to be going over a few more practical elements of parallel computing. So some more examples, some more uh, ideas about best practices and things like that when you are actually going to sit down and try to implement these ideas to improve your workflow on the HPC. So with that said, let's get into it. And I'll just remind everybody that if you have any questions throughout the workshop, feel free to, if you're here in person, raise your hand. If you're on Zoom, either drop it in the chat or, unmute yourself. That should be fine. And yeah, let's continue on. So just very basic reminder about what is parallel computing. So last week we went over more details here, but just to kind of give the broad strokes overview, serial computing, the idea behind this is when you have a problem, you can break this problem down into discrete sets of instructions, or sorry, a discrete set of instructions, and then each of those elements is then fed one at a time in order to a single processor. So this is sort of the classical idea of computing when you only have one processor and one set of instructions. In parallel computing, on the other hand, we have still one problem, but this problem can be segmented into chunks. Those chunks can then be segmented into instructions, which can then be fed into processors, multiple at the same time. So of course, parallel computing requires multiple processors in order to achieve this. So you have multiple instruction streams being fed into multiple processors that can be solved concurrently, so at the same time. Just check on something real quick. Okay, so just to give an overview here, how does a researcher such as yourself implement parallelization in their code? So in this presentation, we'll go through a handful of different cases for parallelization. The first being that in many cases, parallelization is already implemented in a particular software or in a particular language, and only configuration on the user end is needed. This is the most straightforward version of parallelization because you don't have to worry about programming parallel algorithms and worrying about details of interprocessor communication and things like that. The second case is going to be that parallelization libraries are available, but not implemented, and this means that user programming is required. This is probably going to be more the case if you're developing your own software rather than using software that exists somewhere, by a collaborator or other researcher. So these are going to be the two main cases that we'll look through. We're not going to discuss coding MPI directly. This can be very complicated and is usually implemented by research software developers or engineers rather than research code end users. So most of us using the HPC would fall into that second category of a research code end user, somebody that downloads something from GitHub, installs it, etc., rather than somebody who is spending most of their time doing the software development side of things. We will cover some simple examples of MPI bindings in Python because these provide wrappers that make things a little bit simpler for the programmer. So there are cases here where it might be possible for us to cover some examples of implementing these ideas directly, but it might be through a library that provides more high-level implementations of these processes that MPI has. So we'll cover a few different other ideas, the idea of parallelization in a program, i.e. a software, something that you have downloaded. This might be, um, something that you've downloaded from GitHub to do a particular task. It could be a genome sequencing software, or it could be a hydrodynamics fluid solver. It could be a lot of different things. So that's the program versus the language, right? So parallelization in language would be a lower level implementation, something like directly programming parallel in C, right? Or in Python, or in whatever language you're using. So we'll try to distinguish those ideas. And just to remind you about the different forms of parallelism as we go forward, we talked about this a little bit last week. So if you want more details on this, check out that presentation. Shared memory parallelism is the idea that you have a lot of CPUs that are all connected to one memory bank so that they can share that memory. So this makes interprocessor communication much simpler. And this would exist as a single node. So on Puma, for example, you have 94 CPUs on a single node. So you can have shared memory parallelism of up to 94 CPUs. If you want to go beyond that, we have to implement something called distributed memory parallelism. So this is multi-node parallelism, where you have CPUs distributed across many different nodes. Each node has its own local memory, but the processor on node A has a different memory bank than the processor on node B. So if they want to collaborate on a task together, they need to pass messages between each other in order to share the information that they have available. So that becomes quite a bit more complex when you're doing distributed memory parallelism. So software and languages, there are examples of tons of different codes with parallel configuration. Each program has its own syntax and set of options. So just to list off a few that I've seen users on the HPC use, and these are fairly popular programs. COMSOL is a physics program, VASP, NAMD, Wien2K, MOLCAS, these are all in the vicinity of molecular dynamics programs. There are tons of others. I'm not going to be able to list them all. I'm not going to be able to go through all of them in detail. So these are either installed on the HPC as modules, or they can be downloaded. So my main recommendation here, read the manual, try the examples, because they might have parallelism that's already implemented that you can leverage with a few simple configuration options, or maybe more than a few not so simple configuration options. It kind of depends on the software. But just to give you a preview of some languages and tools that we'll mention here. So array jobs, something we'll talk about. GNU Parallel is a parallelization library that's implemented in the GNU software suite. There's Python. We have multiprocessing and MPI for Pi. We'll go through these in a bit of detail, so we'll have some examples for those. There are also programming languages like Julia and Chapel that have native parallelization, and other popular languages or tools like MATLAB and R that have libraries available to them that users can implement in order to achieve parallelization. Or they might already have software packages that have been developed by other users that implement those libraries in order to enable you to run your analysis in parallel. Okay, so let's just quickly go through some best practices. So these will be good to keep in mind as we go through the rest of this presentation and as you are thinking about implementing these for your own workflow. So first is read the manual and documentation. This is always number one for any software thing. Try the examples. Many research software out there is very well documented and has plenty of examples for you to try on your own. So before trying to implement it in your research workflow, try out the examples, see how it works. I can't recommend this enough. It'll cause you much more of a headache down the road if you try to jump into complex parallelization techniques directly implemented in your research workflow without having read the manual or without having tried the examples. So also keep detailed notes and records if and when you do decide to implement these techniques in your own research. It's important to, save an older version of your code so that you don't lose any work if something that you implement doesn't work out the way you planned it to. Keep detailed notes and records about the changes that you've made and about the effects of those changes. Use existing packages when possible. So, you don't have to reinvent the wheel every time. So if you are looking for a software package that does a particular thing, you don't necessarily have to rewrite that from scratch. You can find it on the internet or from a collaborator and implement that in your research workflow. If somebody's already written an algorithm to do shotgun genome sequencing in R that it implements parallelism, this is something that you could just go download and use rather than trying to implement that on your own. As fun as that is, that could be maybe a side project if you really are interested. But this is an important one. Test extensively. At the very least, you should be comparing a serial implementation versus a parallelized implementation. And, this could be either code that you've written or code that you've downloaded, and you're testing, you pass the flag, all right, do parallel now, and see if that actually works better than you expect it to. So as you're implementing these things, testing is very important. This is related to number 2, keep detailed notes and records of these things. If different parallel implementations are possible, then compare different implementations, compare how it scales. Maybe this program works very well in shared memory parallelism when you're implementing it on a single node. And then when you scale up to multi-node, perhaps the communication overhead from multi-node parallelism causes a decrease in performance. So these are just things to be aware of, and testing extensively is a best practice that we highly recommend. And lastly would be to review your job's performance metrics. So we have a command on the cluster, SEFF. If you pass a job ID to this, it will tell you some basic statistics about the CPU efficiency as well as the memory efficiency. We talked about this a little bit more in our workshop on managing and optimizing jobs. So when you go back and, if I've run my code in parallel and I've requested, say, a full node, and then I look at the Ceph efficiency report and it says that it only used 10% of the CPU efficiency, well, that tells me that something's going wrong in the parallel implementation. It could be either that I haven't configured it quite right. It could be that maybe there's only a small section of that code that's actually able to be run in parallel and the rest of it is being run in serial. So it might not be a bad idea to split that up into, here's the serial portion. We're going to only use one CPU on the cluster because that's all it could possibly use. And here's the parallel portion, and we're going to request multiple CPUs for this job, right? So there's a large number of different things that could affect your job's performance. So this is why doing all of the above here is highly recommended as you're implementing new parallelization techniques in your workflow. So let's talk briefly about MPI, just because this is a very commonly used set of standards. So MPI stands for Message Passing Interface. It is a standard for interprocessor communication defined and developed in the 90s and has become basically the default implementation for any type of multi-node distributed memory parallelism. And it's built around the notion of a communicator within a message passing model. So a group of processes, each with a rank, that communicate with each other explicitly. I can have process A sends a message to process B, and that process then receives it and does something with that data. An important note here is that MPI itself isn't a code, but a protocol. There are many implementations of MPI. So we have several of these on the HPC cluster: OpenMPI, Intel MPI, MPI-CH. MPI for Pi is a set of bindings for Python. So this is effectively what MPI is. So when we're talking about that, we're talking about distributed memory computing. So remember, multi-node. MPI isn't really necessary for shared memory parallelism because remember that those processors all have that shared memory bank. So they have the communication between those processors doesn't always necessarily need to be explicitly implemented with MPI. So there's a few different ways that processes can talk to each other. So the very basic one would be to send and receive. So collective communications define types of communication between multiple processes. Point-to-point communication would be any communication between two individual processes. So process A to process B directly, no other processes are involved. Most programs involve some kind of hybrid of the two. And of course, there are many more advanced features, but here the image you're seeing is a visual representation of a handful of different collective communication schemes in MPI. So you can see broadcast there. You have a processor that's taking its data and sending it to all other processors. Scatter is similar to broadcast in a way, but you have different components of that data that are then being individually sent to different processors. So the processes that are receiving it aren't receiving the full amount of data. You could imagine a case like matrix multiplication where that would be useful. The main process has the full matrix, and then each individual operation of that matrix multiplication gets then sent to a sub-process or another processor, right? And then you can see gather, where you're pulling in information from different processes, reduction, where you're summing up all of those individual pieces of data to have just one piece of aggregate data there. Here is an example of a trivial MPI program implemented in C. So I have a resource on the bottom there. So keep an eye out on the bottom right of the screen. Sometimes I've included links there to resources that might be helpful for you. So this is a very trivial MPI program that just calls MPI init, prints that it's running a multiprocessor code, and then finalizes it. Nothing too complicated there, but also nothing terribly useful either. This is just to note that many programs using MPI need to also use a special MPI compiler. So if you are writing in C, you would need to use MPI CC or Fortran MPI F90. And when these programs are compiled with MPI, they need to be executed with the proper function calls. So if you're running a program that implements MPI, rather than simply calling the executable directly, you'll need to pass a line of code that looks something like this, where you've invoked MPI run and passed a certain number of processors to it. So NP number of processors, and 16, that number could be whatever number of processes you have in your job. And then the executable is called. So here is a much more complicated message passing example, still relatively trivial as far as MPI goes, because we're just sending and receiving some calls. I've highlighted the sections of the code that are of interest. So just going kind of in order, I'll just read through them. We don't have to fully understand everything that's going on here. But just to demonstrate the different components of MPI, the first thing that's always called is that blue line there, MPI init. And then you have MPI com rank and com size. These are other initialization processes that happen. And when you have a processor of rank 0, that's sort of the master process. And you can see within that master process, you have an MPI send. So there you're taking a value for whatever's going on, and you're communicating it to a different process. So you can see within that for loop, that MPI send is being communicated to all other processes. And then in the else block on the right-hand side, all other processes of rank higher than 0 will then receive the value that is communicated to them through that MPI send call. So you can see that this, if you want to do anything more complex than just pass values around, then the MPI code can get more complicated. And there are more complex functions than just send and receive. Those would be examples of point-to-point communication, right? We talked about that back here. Point-to-point communication, only 2 processors. MPI also has a large suite of collective communications protocols that are useful. And then MPI finalize called there at the very end. So this is just to demonstrate that MPI has all of these sort of functions built into it. And depending on which implementation of MPI you're using, they might work better or worse given the particular hardware that you are using. So there's also a hardware aspect to this that we're not going to get into at all. So if you're interested in MPI, there are tons of tutorials and resources online, but this is not a workshop on research software engineering. We're going to try to get to something a little bit more practical that researchers can think about as they're implementing code in whatever field you might be working in. So check out these resources here if this is interesting to you. Otherwise, we're going to move on. So most researchers will really only encounter MPI when you're using existing codes that have already been implemented with it. So most cases for the end user would look something like download the code from GitHub, reading the documentation, perform your setup and configuration as described in the documentation, and then executing the program. So here's an example of a code called a repo. This is one that I used extensively in my own history. A repo is a moving mesh gravitational hydrodynamics solver used in astrophysical simulations. So here that's an example of some kind of fluid flow being represented in a repo. It was written in C and uses libraries for MPI. So depending on your system, you might want to use OpenMPI, MPitch. These are backends for all of those function calls that we saw earlier. To run the code with an existing executable, so this is assuming that you've already configured and compiled your executable, the code to run that would look something like this. So MPI run, pass a number of processes. In this case, we said 32. A repo is the executable. That's just assuming that that is some executable program that lives in the current folder that you're working in, and then some parameter file that we've called param.txt. So that's like a set of arguments that gets passed into the executable. So this isn't just the case for a repo. This is a very common workflow case for implementing code that has, or for running code that has already been implemented using MPI. So on the user side, it is required for you to compile that executable and to construct the parameter file. So this, of course, varies widely depending on the exact nature of the program that you're using. But the parallel execution is as simple as invoking this MPI run command. So there are a handful of different things that the user needs to be aware of, but you don't need to go and actually write those communication protocols into your program. They've already been done for you, and you need to compile and execute with this command here. So yeah, just to generalize, there are many research codes that have this formula. First step, compile. Second step, configure. Third step, execute. And sometimes options for parallelization are extensive and complicated. Other times they're a little bit more straightforward. So again, research codes vary widely, so read your documentation. But many times you can get away with implementing advanced parallelization techniques that have already been implemented for you without too much complicated configuration on the user end. So yes, again, read your documentation. Okay, so that's talking about running programs that have MPI already implemented in them. I wanted to talk about array jobs in here, and I wanted to talk about them because they are a way for users to achieve a form of parallelization that's not explicitly implemented in the code. So you could imagine if I'm running, say, so for example, Python is a natively serialized language. Whenever you run a Python program, unless you've made the configuration and coded everything into it to be parallel, so barring that, just default Python is going to be standardly serialized, so meaning only one process for that code. So let's say I have 10,000 different data sets that I want to run a Python script on. Rather than running them all in order, we can achieve sort of a level of parallelization that goes above the level of code, right? So each individual execution of that code is serial, but because I have a large number of data sets, I can achieve a level of parallelization through just running a large number of jobs simultaneously on the HPC. So that's one level that we can use that. So exactly here, the array jobs are useful if you have to run the same analysis on many different data sets. Particularly if the order of completion does not matter, but it is possible also to implement things like dependencies that allow you to run array jobs where the order of completion does matter. So check out our documentation on doing that, but we'll go over a simple example here. One thing to note, don't use for loops to submit a large number of jobs. This can cause problems with the scheduler. So instead, we use arrays to submit a large number of jobs. It might be tempting because it's sort of easy to conceptualize, oh, for I in range 10 S batch this program, right? That's not what we want to do because that can cause problems for the scheduler when a large number of jobs are all submitted within a very short time frame. So instead, we use arrays because that'll allow the scheduler to figure out where those jobs should go rather than overwhelming it with a large number of requests all at the same time. So we see here at the top, instead of this, so there, that first line of code is an example of a for loop to submit jobs. So don't do that. If this looks familiar to you, if this is something you've done before, we recommend switching your workflow over to incorporating array jobs. So instead of multiple batch scripts, you only need to write one. So it does make things simpler for the user as well in the long run. So the second block of code that you see there with all of the batch directives, this is an example of an array job, a very simple array job in Slurm. So you see there, the bottommost batch directive says -- array 1 to 10. And then within there, or sorry, directly below that, you have a command, echo sample input file, and then it's passing a variable slurm array task ID. So that's replacing that variable call with the number associated with that array. So we have array 1 to 10. So in this case, we're assuming that we have input file 1, input file 2. Those numbers get substituted for the array task ID within Slurm. So if you have your data sets enumerated, and you can call them whatever you want. It can be 537 to 547 if you wanted. It doesn't have to be 1 to 10. So you can adjust them as necessary for your workflow. So just a reminder, don't do the for loop thing. That's not to tell you to go do that. That's to tell you don't do that. So instead, use the array jobs, please. So here's an example of an array job with MPI. So in this case, I've highlighted a few of the batch directives there. So the first one, n tasks equals 30. That would be the total number of CPUs available. And when you're submitting an array job also, just to note, any of the batch directives that you request, that is the number that get requested per job. So it's not a global thing. This is each job gets executed according to the directives that are in the batch script. So, so in this case, we're doing a multi-node job. So we have 30 tasks, 3 nodes, and 10 tasks per node. So that means each node that we have ends up with 10 CPUs for a total of 30 CPUs. And then the code down there, you can see we're loading the modules that we need. We're compiling the program, hello world, with MPI-CC, and then we're executing it with the MPI run command. And just as a note, this is an example. The numbers that I've included here are not recommended to use. There's really no good reason to use less than the maximum number of cores per node. So on Puma, you have 94 CPUs. If you really needed to use 30 CPUs for this job, then there would be no reason to do multi-node, to request more than one nodes, right? So on Puma, 94 CPUs. If you need 188 CPUs, then sure, request two nodes, right? But if you need 90 CPUs, there would be no good reason to request 30 CPUs across three nodes, right? The reason for this is that multi-node communication is, of course, as we discussed, complex and requires some overhead. So that's some initial processes that need to run at the beginning of a program in order to establish the multi-node communication. So if you don't need to do that, there's not really a good reason to. So if you can run something on a single node using shared memory parallelism, that's always recommended over multi-node parallelism, given the same number of cores, right? So if you really need to scale up and use a large number of nodes for your work, then distributed memory parallelism is great for these large scale jobs. But in the case where it's a smaller scale, there's no reason to spread cores out over multiple nodes. So we're just going to keep going through a handful of different examples here, each one at a time. And just as a reminder, if you have any questions along the way, feel free to let me know. So GNU Parallel is a nice little tool that's available. We have it installed as a module. So in order to access it, you would request module load parallel, and then you can use the parallel command as follows to execute different tasks, right? So in this case, the code that you're seeing there is we're accessing the Elgato cluster. We're starting an interactive session with 8 processes or 8 CPUs. We're loading that parallel module, and then we're performing this command sequence 1 to 100, parallel, print out the date, do some things. And basically what you have here is the output of the command at the bottom. You're listing the host that you're on, and you are seeing there basically the rank of each individual process that gets, or sorry, not the rank of each process, but the sequence in the order of this command. I hope that makes sense.
Hey, Ethan.
Yes.
There's a question in the chat about an array job. You might want to look at. I don't see the actual error on there, but they're getting an error when they submit an array job.
Okay. Yeah, this is maybe something that you can reach out to us later on for us to look in more detail with. If you have a question about something that I've said or something related directly to this presentation, I'd be happy to answer that. But if you're in the middle of doing some work and you need some help with that, I recommend reaching out to our HPC consult team. So there's ways of doing that. There's ServiceNow. Maybe Chris, you can drop the ServiceNow link in the chat. So
Yes, sure.
yeah, thank you. So yeah, I'm happy to provide clarification, but for more detailed questions, definitely that'll be something that we'll have to do one-on-one later on. Okay, so but I appreciate you for asking, and this is certainly what we're here for to help with. So some more possible ways of using GNU Parallel. First example here shows that Parallel can create as many jobs as inputs. So I have my inputs here are A, B, C, D, E, each.txt. So I'm passing some files there, and I'm echoing the process number for each of those. And you can also see in the second one that I've limited the number of jobs to 2. So in this case, I have the same inputs, but rather what I'm doing here is printing the process number. So same idea, but you can see in the output that there's only 2 processes that are being executed rather than 5. So, you know, if you're running a job on the cluster and you've requested 8 CPUs, then you might want to limit your parallel execution to 8 in that case, because it wouldn't be possible for it to create more jobs than processors that you have. So link at the bottom there for more GNU parallel examples. This is a very handy tool for doing a lot of different things, very widely applicable for a lot of different cases. So here's an example of using an array job with GNU parallel. So in this case, we're doing two arrays, so array 1 to 2. So we have basically two jobs that get executed. And you can see at the top there, the second batch directive and tasks equals 94. So this would be a full node on Puma. So each of these arrays is using an entire node on the Puma cluster. And we'll just kind of go through each thing individually here. So I've defined a block size of being 200. And I'm just going to print this part out at the right-hand side of the screen so we can see what's going on. So this is creating a sequence. So for array job number 1, it's creating a sequence of 1 to 200. And for array job number 2, it's creating a sequence of 201 to 400. So in this case, I'm able to process 400 files with two array jobs, each of which is processing half of those files, right? So we won't worry about parsing the math exactly, but the idea here is that we can take a large chunk of information, break it down into smaller chunks using both arrays and GNU parallel. And the place where GNU parallel comes in is that this sequence is being piped into it at the very end there. And it's, so we saw previously where that sequence command was used to initiate parallel job. So in this case, when we're creating sequence 1 to 200, we're able to use GNU parallel to execute some command with those tasks. Yes.
No, sorry if I missed that. What is the benefit of breaking down into like multiple array jobs?
So in this case, I would say that the benefit is that you're able to, so if I wanted to execute this with a large number of processors, right? I have 94 processors requested here. That is the maximum number of processes that you can get on a single node in Puma. So without implementing something like MPI to do internode communication, how can I then speed up this execution? So if I didn't use an array job, I could still certainly do sequence 1 to 400 on this, but that would take twice as long.
Oh, so
yeah.
Each array job will request one more.
Exactly. So now we're having each array job has a full node that is available to it that it can then use to break it down into sections, right? Yes. Yeah. So this is sort of a way of doing some task using multiple nodes without having to communicate in between. And of course, this requires that whatever task you're doing, actually, that whatever job I'm performing on one node doesn't depend on the result of a job from another node. So this would be independent work. So that this is a good example of doing something like this for independent work. If the work is dependent on one another, then this is more complicated and you'll need to do some sort of multi-node communication thing. But yeah. So just to demonstrate how this would work, so we are now submitting that array job. So back here, this batch script that we're looking at is being submitted to the cluster. It says we've submitted a batch job, and then it's creating certain output files. So we can see here that there are two output files, each from one of those array jobs. And just looking at the first 5 lines of each of those output files, you can see that the first output file is going through inputs 1 to 5, and then the second output file is starting at input 200 and moving from there. And this is just the top section of the output files. Of course, if you were to go look at the full file, you would see 1 to 200 in the first, and then 200 to 400 in the second one. All right, so that is array jobs and GNU parallel. These are maybe tasks that can be performed on the cluster as a way of, breaking jobs up into smaller tasks. So here in Python, we're going to go through a handful of different examples. So Python, very commonly used language. Many researchers use this language. I've used it. I know it's used widely in many different fields. And the things that we're talking about here might also be applicable to other languages as well. But we're going to get into using two libraries for parallelism in Python. The first that we'll talk about is this one called multiprocessing. So this is the default library for shared memory parallelism. So Python has this thing called the global interpreter lock that forces it to be serialized. We have a question in the chat here, so let me read this out. It says, what happens if a node errors out / fails during execution of a job? Does the job get rescheduled? Also, is the job maintained? So if you have some error that occurs during a job, the job will fail and it will not get rescheduled. This is something that you'll have to do manually. The job state is not maintained. And the reason for this is that if there is an error, if the program is encountering something that's going wrong during its execution, you don't want to save that erroneous state to then restart it and then get it locked into a loop where a bad execution is being run again and again. So if there's an error during a job, you'll need to go look at that error, fix it, and then resubmit. So thanks for your question. So continuing with my Python multiprocessing. The main components here, we have process and pool. Those are like the two main ones. When we look at an example, those are what we'll be using. There are other components such as queue and pipe that allow for interprocess communication, and then other primitives that manage access to shared resources below. So we're not going to get into all of the details of these. We're going to go through a relatively simple example. So MPI for Pi is a non-default library. So just to contrast those, multiprocessing is a default library. You don't need to install it. It should be in Python by default. MPI for Pi, on the other hand, if you want to use it, you will need to install it. And this enables distributed memory computing across multiple nodes by implementing MPI. So there's a handful of different components available here. Again, we're not going to get into the details of all of these. So the example that we're going to go through here is to do an approximation of pi with a Monte Carlo simulation. So the idea here is that we're going to, you can imagine throwing darts at this square. You can determine whether a dart is on the circle or outside of the circle. And the area of the square is going to be proportional to the number of dots inside of the square. The area of the circle is going to be proportional to the number of dots inside of that circle. And then by getting the ratio of those areas, you can see the math there below the image on the left. We can approximate pi by taking the ratio of the number of points in the circle to the number of points in the square and multiplying it by 4. So that's what we're going to be doing. And this is a great task for parallelization because it doesn't matter what order those points are put down. It only matters the total number of points that are inside of the circle or outside of the circle. So you can see on the right there that you can break that task down into 4 subtasks and then add up the results at the end. So that's what we're going to be doing. So just a note on libraries before we get into this with Python. Before we write any parallel code, we'll need to set up an environment that contains the proper libraries. So for us, MPI for Pi is going to be the library that we need. And just as a note on this, setting up environments for specific purposes is a highly recommended practice. I don't recommend using one catch-all environment. This might be tempting because then it means that you have to manage fewer environments, but the environment that you have to manage then is much more complicated. And this can lead to things like conflicts or version issues. So we'll get into the details of best practices relating to environments next week. But this is just a simple note here to manage this. So here's a walkthrough of how you might do that. And I don't want to take too much time on this. So if you want to go through this and perform this exercise, we can come back to this at another time. So you can see the link on the bottom right there. Our documentation has a full guide on installing Python packages. And here on screen, you see the commands that would be necessary in order to create a environment that contains MPI for Pi. And in this case, I'm using pip to install the package. So here's a repository of some code that I've developed for this exercise. So you can go clone that into a directory on your HPC account. We'll go through and look at some of this code. So in the next handful of slides, we're going to be looking at that code directly. If you want to run it, you can download this repository from GitHub and try it out for yourself. So let's just go ahead and look at the code. So here's the code for the Monte Carlo simulation. So this is creating a point, placing it on the circle, and counting the total number of points that end up inside of that circle. So pretty straightforward. And I'm going to just give you a note here as we're going through. We're not trying to understand every detail of every bit of the code that ends up on the screen. We're just going to try and get out the important sections. So you can see my mouse there. This is the serial execution of this calculation. So we can see that we're running 1 million points, so 10 to the 6. And we are getting the final circle count by executing the Monte Carlo simulation that we just looked at on the previous slide. We're calculating pi by performing this equation, 4 times the number of points in the circle divided by the total number of points. And then this will print out all of the statistics about the job as well. So this is the serial execution. Not much to talk about there. The batch script, we're requesting 1 node with 1 task, and we're simply executing that Python command. So in here, it's also important to note that I have loaded the module of Python 3.11, and I have sourced my personal environment that I just created that contains the MPI for Pi code. So those are important steps as well. But the serial execution involves just requesting 1 task and executing that serial code as normal. And here's the output. So we ran the serial version of PyCalc. It took about 10 seconds to complete, and we ended up with a % error of 0.02%. So pretty good. Obviously, it's not exactly pi to a large number of decimal places, but we at least got the first 2 decimal places, and we're not far off. So that's pretty good. So let's see what kind of performance we can get by implementing this with the multiprocessing library. So remember, multiprocessing is a default library of Python. You don't need to go download and install it. It should be there already. And with this library, we can use single node shared memory parallelism. So looking at the code here, we have this master worker pi calculation. So within this function, I've included things like pool, and this allows you to handle the interprocessor communication without much effort from the end user. So we're basically taking this task, the Monte Carlo simulation, we're mapping it onto the pool and passing it the number of points that it needs to execute, right? And then these last couple of lines here, pool.close and pool.join, effectively just aggregates the results from all of the different processes. So you can see here, I'm not doing things like calling processor A sends a message to processor B. this isn't necessary with multiprocessing. Was there a question?
Yeah, so processor still means CPU.
Yes.
We're not,
Say that second part
we're
again.
not-
No, we're not handling multi-node situations here. So all of these processors would be individual CPUs on a single node. So in this case, the user doesn't have to explicitly program sends and receives. We just take a function, we say pool.map, and it does all of the backend for us. So that's pretty convenient. Here now we have, I just want to point out, total circle count is equal to master worker pi calculation. So that's the one that we just did. And then the rest of it is exactly the same as we saw in the serial version. So in this case, we're just calling that function that does the multiprocessing and getting our total circle count from that. And then we see in the batch script here at the very bottom, I've called this by using Python 3 and the name of the script. So there's no special MPI that needs to be invoked here. We're just using Python 3 and the name of the script to call that. And then I'll also point out in the middle here, CPUs per task is equal to 8. So you can change that to see how the behavior changes. So of course, that number needs to be less than or equal to the total number of processors on a single node. So in this case, we'll still just need to have, a single node. And here's the output. So we're running the multiprocessing version. It says working on 8 processors. And we can see here that the time taken to completion is, 1.5 or about 1.6 seconds, which is much less than the 10 seconds that it took to run it in the serial version. So we are actually experiencing a speed up, and the result is pretty close to the result that we got in the previous version. So you can see in this one, we could potentially increase the number of points that we're calculating with in order to get a much more accurate answer if we wanted to use the same amount of time that it took to run the serial version. So there's different types of scaling involved with this. So if you want to hear more about different ways of code scaling, last week's presentation covered that. But for now, we're going to move on to the MPI for Pi version. So you can see here, there's these very explicit communicators that get called when using MPI for Pi. So we're sending and receiving signals between processors. Again, not going to worry too much about the details, especially since we only have a few minutes left. But the point here is that when using MPI, there are much more explicit calls that we have to create. So compare this to the master worker pi calculation from multiprocessing, where we basically just had to call this pool thing and then it handle all of the communication for us on the back end. In this case, we are more explicitly programming in that communication. And then again, here, so processor rank 0 gets called for the master worker pi calculation. And then we're passing it the number of tasks from Slurm. There's that main calculation. And here's our batch script. So there are a few things that I want to point out here. Just in the batch directive section, we are requesting 3 nodes. We're requesting a total of 12 processors. And this line here, n tasks per node, this isn't strictly necessary, but if we want to split the tasks evenly across the nodes, then this would be something that we should do. So n tasks per node is equal to 4 in this case. So we have 12 CPUs spread across 3 nodes, each node with 4 CPUs. So going down here to the code section, there's one additional thing under the module load Python, which is module load open MPI 3. So that's required in order to actually have MPI work, right? And this is a module that's loaded by default, but it's, for me, I think just loading the modules that you need in the batch script explicitly is good practice. And then you can see at the bottom here, the function invocation is very different. So now we're including the MPI run, and we're passing it the total number of tasks. So slurm n tasks here would correspond to this number 12. And then we're calling Python 3 PyCalc multiprocessing. So there's a few more steps that that are necessary in order to fully utilize MPI. So here's the output you see on the right-hand side. This is just a small section. The program was executed numerous times. So what you're seeing here is that section of the code that's outputting the result, but it's being output multiple times. So the problem here is that the master calculation was included in the script that was called with MPI run. There could be a cleaner way of doing this in which the master calculation is invoked elsewhere. The MPI is just called to generate those points, and then the output of those tasks individually is then performed in serial in order to avoid the master section being called multiple times. So this is just to say that care needs to be taken to separate master tasks that only need to be run once from subtasks that are distributed to different processors. And that's about it for MPI for Pi and Python. So I'm just going to quickly breeze through a couple of slides here just to give you a broad strokes overview of them. If you are interested in looking more in detail at the code, these slides are available. I sent them out via email, and they'll be also available on our documentation. So check that out. So there are a handful of different packages for R parallelism. We won't, of course, get into the details, but these do exist. So R parallel, built-in package, most commonly used. There are also things like for each and do parallel that offer flexible parallel loops. So here are some functions that are implemented in R. So these, as you can tell, are very different than the functions that are available in Python. So whichever language that you're using, you'll need to sort of understand what these parallel implementations are actually doing. So the MCLapply, that's in a way similar to the pool thing that we were using with multiprocessing, but there's all sorts of different implementations of this. So here's the pi calculation implemented in R. So here's the Monte Carlo simulation, same function that was being performed as before. Here's the serial version of that implemented in R. And then here is a parallel version implemented also in R. So one important thing to note with parallelism in R is that Python has MPI for Pi, which enables multi-node parallelism. R does not have that, so all of the parallel libraries in R are for shared memory parallelism rather than distributed memory parallelism. But you can see here again that we do see a speed up of about 5.5 times when implementing parallelization in R. Here's a page full of R resources for you to check out. And then other common languages, Julia, MATLAB, Chapel, all of these have their own versions of these parallel tools that we saw. Of course, not possible to cover all of them, but many softwares out there provide documentation and examples for parallel execution. So hopefully this has given you a broad strokes overview of the different ways that parallelization is implemented in order for you to be able to understand the documentation for your particular use case and to, I don't know, get involved with that more directly. Here are a few additional resources. So the Lawrence Livermore Introduction to Parallel Computing tutorial is excellent. If you go there, you'll see that we've pulled quite a lot of material from it for our training sessions as well. And then additional recommended reading below there, lots of great textbooks or other online resources for you to check out related to parallel programming. And with that, thank you for listening. Thank you for attending, everybody. We'll hang on for a few minutes to answer any questions. But I'll stop that recording now. So yeah, thanks again for watching.